This illustration deals with short circuit and ground fault protection in accordance with 240.92 C1 Item 1 through C1 Item 3. C is in car. Now, before we really get into this illustration, I'd like to look at the design tip with the information that we have presented here. And we're considering a 2500 kVA transformer with an impedance of 5.75% with a voltage of 13,008 kV or 13.8 kV. The secondary is 480/277 volt, and that's our ratio. We have a 500 MVA available short circuit current on the primary, a 100 circuit feed of a 300 amp cable bus with a three-phase bolted fault occurring at the end of the bus, the worst case. About 38,937 amps will flow from the system, or 1,352 amps on the primary, which will clear a typical 150 E fuse and meet the minimums of the 150% requirement within 0.42 seconds. Now, this time versus current value is well within the rating of the secondary conductors. The cable bus has a resistance now of 0.001819, and the transformer has a resistance of 0.005295. Now, this information is given to you. It was collected, and if you want to read more about it, then see Figure 20-41 in Stallcup's Volume 2 of the Electrical Design book. Now, we're going to look at the quick calc next. We have 480 volt secondary divided by 13,800 times 3,000 now. And remember, 3,000 amp is your cable bus. Times 150%, we come up with 156 amp. Now, there's no exception over here in this supervised industrial location located in 240.92 that would allow you to round up, so we're rounding down to 150. Look at the protective device on the primary side. The 150% rule or less to the secondary to primary voltage ratio is met here. We haven't exceeded the 150% there if we had a 150 amp main. Now, off of the secondary, we're going to make this transformer secondary tap with transformer secondary conductors over 25 foot up to 100 foot to comply, to start with 240.92 C11. Now, to apply the minimums here, we would look at the boxed in information to the right of the illustration, and the secondary full load current, 2,500 kVA times 1,000 divided by 480 times the square root of 3, gives us a full load amp rating of 3,008 amp. That will supply under normal operating conditions without any voltage drop, correction factors, adjustment factors being made. That will naturally take care of the 3,000 amp bus. Now, what is the short circuit current? Well, we would find that 308 amps is what the output, or I quoted that wrong, 3,008 amps divided by 0.0575, which is your impedance. We'd come up then with a short circuit current of 52,313 amps. Now, amps at the fault, The transformer would be 0.005295 would be the resistance of the transformer if we did our math and so forth to ground. The cable bus now, we listed that for you in the design tip, and it's 0.001819 is the resistance. These two have to be added together for this rule of thumb method. And we would come up then with 0.007114 is our resistance. Now we're going to take that total resistance to the secondary ground voltage of that 480-277, which would be 277. Now we divide that total resistance into that, and we come up with 38,937 amps. Next step is your D factor due to the ratio. So we have to take the primary at 13,800, divide by the secondary, which is 480, and the ratio is 28.8. Then we would take that available short circuit current of 13,800, and we would take that primary, and when we take that primary ratio of the 13,800 volts, divided by 480 volts, we come up with that 28.8. But now we would take the short circuit current of 38,937 amps at the fault, divide it by 28.8, which is on the secondary side, and we would come up with the ratio of amps to the primary side to clear that 150 amp device. We would find 1,352 amps. Now the IEEE Green Book, along with the IEEE book dealing with overcurrent devices, suggests on that high voltage you to have 5 to 6 times. And even if we use 6 times 150, that's only 900 and something amps. So we have a lot enough amps to clear that primary using this good rule of thumb method. And that's what the note at the very bottom of the primary short circuit current states. 1,352 amps clears 150 amp E-type fuse that we see listed on the primary side of that overcurrent protection that we see there. So with the information given in the design note, this figure 9-33 shows a good rule of thumb method for determining the short circuit and ground fault protection when we apply NEC 240.92 C as in car 11 through C as in car 1 item 3.